For over a year, I've been trying to kill this bone stock Duramax L5P. We've upgraded the air intake, we've gone to a precision turbo, we've got a Banks 5-inch exhaust, we've got an S&S pump, and S&S 100 over injectors. And last week, we put in our Banks-spec Comp cam. Today, I'm going for 1,000 horsepower. Will I kill it in the process? You're about to find out. I'm fogging up my glasses over here. What do you say we build a little heat in this mother? And it's alive. We're in California, we're wearing masks, we're politically correct. What we're going to do in this test is as follows. We're going to have some constants based on the 912 horsepower at 3,400. Here's our constants and limits. 260 bar max cylinder pressure, 1650 EGT, 480 Fahrenheit compressor discharge, 16.2 to 1 max air-fuel ratio, 125,000 RPM turbo shaft speed, and I'm thinking that manifold air pressure will be constant or slightly higher. Manifold air density will be constant or slightly higher, and mass airflow should increase due to the cam change, which enables more RPM. Both of those items will give us more mass flow into the turbocharger and consequently into the engine. Our percent cylinder fill should also increase, crossing my fingers on that one. And of course, the valve open time or duration is increased significantly with our camshaft. Thank you, Comp Cams. Thank you, Billy Godbold. Injection timing, start of injection will be 23 degrees before top dead center. And I have a limit of 40 degrees crank angle for injection. That's 1,750 microseconds nominal on time at 3,800 RPM. How's our lift pump pressure looking? Okay, so we've got a nominal 15 pounds gauge lift pump pressure to that Bosch pump. We're running an S&S, a Bosch-based S&S stroker pump on the engine now, instead of the Denso high pressure pump. So we had to bring the lift pump pressure way down. We were around 90 PSI gauge with a Denso pump. S&S tests their Bosch builds at 15 lift pump pressure. All right, let's bang this turkey. All right, here go the loggers. Okay, Aaron, is this gonna work? Is it gonna be happy? Okay, we're after it. 200, 300. Everything's looking good. All right, boost. Dyno boost pump on. There we go. 800. 850. Come on, 900. Come on, 900. Woo! Come on. 950. 80, 90. Woo! 1,003. 1,003. Oh my God, Jesus. Stock internals. When you guys at GM redesigned this engine, you did something very special. Anybody at GM that was on that team, I would like to shake your hand. Mind-blowing, mind-blowing. The only thing inside that engine that isn't dead stock is the Banks-spec Comp cam. Good job, Billy Godbold. All right, Aaron, let me have the SD card out of that data monster. Wow, 1,004 horsepower. What a way to celebrate the 20th anniversary of the Duramax engine. DMAX Ltd. released their first production engine on July 17, 2000. And here we are, 20 years later with our L5P, one of the most incredibly bulletproof engines I've ever had the pleasure of working on. You guys and gals at DMAX should be so damn proud. So I had a goal. What was that goal? To hit 1,000 horsepower. How were we going to do that? Well, Aaron came up with an idea, and that was, let's run the same torque at 3,800 RPM that we ran at 3,447. That should give us 1,005 horsepower. 1,389 pound-feet at 3,800 RPM was our goal. To get to 1,000 horsepower, we needed to do some upgrades. First was a Banks-spec camshaft to replace the stock L5P cam. Then a 8085 custom precision turbocharger to replace the 7675 precision. A 4-port TurboSmart boost controller. It was a 3-port type. An S&S 12mm stroker CP3 Bosch high-pressure pump replaced the stock Denso pump. We went to S&S 100 over Denso injectors to replace the 50% over S&S injectors. And we raised the rail pressure to 2,400 bar. It was 2,200 bar. Once we installed all this equipment, we decided to set some red lines. The red lines are values you don't want to exceed. So I got together with Aaron and we kind of talked this through. Some of the red lines are self-imposed by us. Some of the red lines have to do with the limits of the equipment we're running. First one is cylinder pressure. We're way over the design of this engine, which is 183 bar maximum cylinder pressure. We've been running around 260, so we set that as a red line for this project. We actually ran 262 bar, just a tad over. Air-fuel ratio, we didn't want to go any richer than 16.2 to 1. In reality, we ran 16.5 to 1, which gives us about 14% excess air above the stoichiometric perfect 14.5 to 1. You have to run leaner than 14.5 to 1 or it's smoke city. 14% isn't quite what I had in mind. I'd have preferred 20 to 25%. Turbine inlet temperature. I don't want to kill the turbine wheel. We set a limit at 1650. We actually ran 1672, so we went a little over that red line as well. Compressor discharge temperature. 480 for short durations. We went a little bit over it because it was a hot day, and we ran 489. Turbo shaft speed, 125,000 RPM, according to Dan at Precision Turbo. We ran 107, real comfortable. And the last one is main injection duration, 40 degrees of crank angle, or crank rotation is my personal limit. We were at 37.4 with a higher rail pressure and the bigger injectors. So let me talk about where all the magic happens, the camshaft. And most importantly, it has to run with stock heads and stock valve gear. In order to hit 1,000 horsepower, I know we need more cam duration. But how do we know how much? It's all about valve timing, and no, you can't get that off a cam specification card because it's not there. Even though the cam spec card says valve timing, it's not referring to time. That's because a cam specification card is not about time at all. It's about tappet or valve lift relative to crank position. It's about the duration expressed in degrees of crankshaft rotation of a valve event. There's an opening point and a closing point expressed by a tappet or valve lift amount and a duration expressed in degrees of crankshaft rotation between those 2 points. That's how engine guys talk camshaft. On the L5P, The intake is 155 degrees at 50 tappet lift. And the exhaust is 166 at 50. But this tells you nothing about how long the valve is open, how many thousandths of a second, or stated differently, how many milliseconds of valve open time the valve duration actually provides. And check this out, for a given duration, the valve open time varies with the RPM, so it's not constant. At 1400 RPM, the valve open times are double what they are at 2800 RPM. All things being equal, longer open times will allow greater power to be produced each time you fire a cylinder. That's why the torque peak occurs where it does. And each cylinder firing produces a power pulse. Let's talk about that. Going from 912 horsepower at 3,447 RPM, that's 230 power pulses per second, to 1,004 horsepower at 3,809 RPM, which is 254 power pulses per second, the power pulses per second went up 10.5%, and we gained 92 horsepower. How do we do that? Well, we did that by making each power pulse at 3,809 RPM equal to the ones at 3,447 RPM. Our path to 1,000 horsepower all started with some camshaft music from Memphis, Tennessee. And I'll tell you, Beale Street never sounded as good as this Banks and Comp Cams jam session. It took a few bars, but the final cut is what enabled everything else to happen. It's all about the valve event clock time. We needed to better or equal the valve open time we were getting running the stock cam at 3,447 RPM and increase our intake and exhaust durations to achieve that open time at 3,809 RPM. The key to all of this is a valve event clock time. Let's run through some numbers here. At 3,447 RPM, that's 57.45 revs per second, and that's 17.4 milliseconds per rev. The valve open time, this is what I'm talking about. The valve open time here is 7.5 milliseconds at 155 degrees duration. We're looking at the intake duration. Just to put into perspective how often this happens per minute, you have to look at the power pulses per minute. And we're at 13,788 power pulses per minute at 3,447. Each rev gives you 4 pulses. So power pulses per minute is 3,447 times 4 pulses per rev, 13,788. Now let's go to 3,809. And you'll notice these are not nice rounded off 3,400, 3,800. This is off of our dyno data. At 3,809 RPM, now we're over 63 revs per second. Our seconds per rev is down to 15.8 milliseconds. And our valve open time has dropped to 6.8 milliseconds. Our power pulses per minute are up to 15,236. We want to make all of those equal to all of those. How do we do that? We adjust the duration of the camshaft. That's how we do that. As we saw up here, at 3,447 RPM, that's 7.5 milliseconds of open time per valve event. At 3,809, that drops to 6.8 milliseconds of open time. So we've lost open time. We need to add 0.7 of a millisecond, or 10.3%, to the cam's duration to equal these out. And this applies to the exhaust duration as well as the intake. On the intake, we were at 155 degrees duration. Multiplying that times 1.103 gives us a new duration of 171 degrees. And on the exhaust, the stock cam duration is 164 degrees. That times our multiplier gives us 181 degrees. I'm not sure you guys grasp just how fast this event is happening. What is 7.5 milliseconds, or 7.5 thousandths of a second? It's way quicker than the blink of an eye. I'll tell you that. It's 2.5% of the blink of an eye. The average blink of an eye is 300 milliseconds, and we're doing this in 2.5% of a blink of an eye. There is your valve open time. There is the blink of an eye. And just so you know, these are not the final duration numbers. Let's just say they got bigger, and I'm not going to tell you what they are, at least not now. Doing the camshaft enabled us to now improve the boosting system. Once again, I'll say we're at a pressure ratio across the compressor in both of these turbos where we can't raise the boost. I wanted to go to a little bit bigger turbocharger to give us more flow range and to match the turbine better to the engine as well. And once again, stock heads and stock valve gear, in fact, everything else inside that engine is bone stock. All boosting starts with ambient air, and we're blessed with being pretty close to sea level, so our ambient air is pretty heavy. The ambient air pressure on both the runs was identical. As far as the ambient air temperature is concerned, Mother Nature was fighting us. We made 1,004 horsepower with a lot hotter ambient air. As far as ambient air, if you're making more horsepower and you're trying to maintain an air-fuel ratio, you got to consume more. So we went from 1,309 to 1,494 cubic feet per minute. Our ambient air density, that 89 degrees kind of hurt us a bit. We went from 72.5 pounds per 1,000 cubic feet to 69.8 pounds per 1,000 cubic feet. That's a density loss where we really would like a density gain. So we've got to make that up somehow. And the last item on this ambient air chart is the ambient horsepower. The iDash is so powerful, it will tell you how much horsepower the ambient air density is responsible for. And since we know the horsepower in both cases, we can calculate a percentage that the ambient air density is responsible for. So 25% of the power output of the engine is attributed to the ambient air density. Now let's go to the cold air intake. Once again, the ambient CFM 1309, 1494 flowing through the system. This setup is using two of our big-ass L5P filters running in parallel. The pressure drop through the system, 0.43 psi, went to 0.49 psi. So about a half a pound of pressure drop. The air temperature gain is slight in both cases, about a degree and a half. The air density loss, 2.3 pounds per thousand at 912, 2.6 pounds per thousand at 1,004. So this density loss is responsible for a loss of 7 horsepower. And this one, 9 horsepower. Expressed as a percentage loss, 0.8% and 0.9%. But bear in mind, with a little ram air like you have in your car, these would be positive values. Now let's start making some serious density. The turbocharger. As you know, we started with a 7675 precision, and we've moved to an 8085, which was custom made at the Precision Custom Shop. The air pressure gain from the inlet to the outlet of the compressor on the turbo went from 47.1 to 46.4. We're trying to hold below that compressor outlet temperature, that 480 Fahrenheit we talked about earlier. The air temperature increase across the compressor was 385, and at 1,004 horsepower, we're knocking on the door of 400 degrees increase. The final compressor out temp went from 458 to 489 with the bigger turbo. Part of that is the hotter ambient air. The compressor efficiency is also a key to these temperatures. At 912 horsepower, this compressor was 73.1% efficient. And with a larger compressor, we were at 71.9%. So a little less compressor efficiency, but still very respectable. So we lost some air density provided by the compressor, but we were protecting the compressor by holding down the pressure ratio and trying to hold to 480 maximum compressor discharge. So even though the air density is lower, we're flowing more of it. Our mass airflow increased from 94.9 pounds per minute to 104.3 pounds per minute. We need that mass flow. The horsepower gain out of the 912 and the 1004, 343 and 370. You kind of look at densities down, mass flows up, we get a greater horsepower bump because the increased mass flow offsets the density drop. The percent of total horsepower that the turbocharger is responsible for, 37.6 and 36.8. Next, let's take a look at the charge air cooler. Now I know a lot of you guys call them intercoolers, and some guys call them aftercoolers, but the all-encompassing term is charge air cooler. For this program, we've been running a Banks prototype air-to-liquid charge air cooler. Looking at the air pressure loss, denser air at 912 horsepower, 2.3 psi loss across the charge air cooler. Less density, 2.1 psi loss across the charge air cooler. This is my limit, right at 2 pounds. That's it. The air temperature reduction, we started with hotter air and we got a greater reduction. 368 here, 387 here. The air density gain, 108.4 pounds, dropping to 107 flat here, virtually the same. There's two ways we look at a charge air cooler. One is effectiveness. What percent of temperature reduction did we get versus what percent of temperature reduction could we have got? 100% being the best you can do. In both cases, we're knocking it out of the park with this prototype. 95.5% here, 96.9 on the higher horsepower. The charge air cooler efficiency also, 83% went to 86%. Charge air cooler efficiency is the bottom line measurement of a charge air cooler's performance. So you'll see me using that term one hell of a lot in public now. So remember the turbocharger horsepower gain? These numbers might sound familiar, 345, 389. The charge air cooler performance is matching the performance of the turbocharger. Are you guys getting this? The charge air cooler is making as much horsepower as the turbocharger. So now let's look at the boosting system altogether. Engine RPM, 912 at 3447, 1004 horsepower at 3809. Boost air density, what I call the bad. Bad is the combination of all the intake system all the way into the intake manifold. So combined together, 213 pounds per thousand and 206.1 pounds per thousand. Next, I want to talk about power pulses per second. I talked about power pulses per minute. This puts it into a more digestible form. We've got 230 power pulses per second at 912 horsepower. We've got 254 at 1004. 230 bytes out of that air density versus 254 bytes out of that air density. So you see, we're cycling the cylinders more frequently here at 3809. Boost air pressure through the whole system, 44.4 versus 43.8. So we're 0.6 of a pound down there. The system pressure ratio, that's working from ambient to the intake manifold, of 408 versus a 404. A lot of you guys read compressor maps and you've seen higher pressure ratios. Well, those are only for the blink of an eye. They're not for sustained running. This program is about sustained running. The density ratio is what I want you to pay attention to. Normally, if you really don't have a decent compressor plus a decent charge air cooler, this density ratio is nowhere near the pressure ratio. But in this case, density ratio damn near matches pressure ratio. And the total system horsepower gain for both these is 688 and 759. So the boost air system is responsible for 75.5% of the horsepower. Remember the air intake lost us some power? Well, that is offset by that half a point. So it all ends up being 100%. Let's talk about the engine now. We've got a boosted engine. What's happening with the engine? Manifold air pressure, as we talked before, 44.4, 43.8. Manifold air temperature, 90 degrees, which is 18 degrees over ambient, versus 101 degrees, which is 12 degrees over that ambient day. The manifold air density, this is the air density in the intake manifold, 286 versus 276, just rounding off the numbers. If you're into turbocharging, you've heard boost to back pressure ratio. This is the math. Compressor outlet pressure minus the compressor inlet pressure. In other words, delta pressure compressor versus turbine inlet pressure minus turbine outlet pressure. So delta pressure turbine minus 1 times 100 to get us a percentage. It will come out signed negative or positive depending on whether or not the turbine inlet pressure is higher or lower than the compressor outlet pressure. Next one is engine scavenge ratio. What's happening with the turbocharger and the rest of the piping impresses itself on the engine. Engine scavenge ratio is a comparison of the intake port or intake manifold pressure and the exhaust port or exhaust manifold pressure. So basically the formula is intake manifold air pressure gauge, PSI gauge, divided by exhaust manifold pressure in PSI gauge minus 1 times 100%. If the exhaust manifold pressure is higher than the intake manifold pressure, this will be a negative percentage. The final one is the cylinder fill percentage. This is the cylinder air density divided by the manifold air density times 100%. Boost air, engine scavenge, cylinder fill percentage. And no, I'm not available as a substitute teacher for shop classes. Looking at boost to back pressure ratio, we've got a negative 1.4%. That means the delta P turbine exceeds the delta P compressor, and you're a little bit upside down. In other words, if it's 0, then they're both equal. What we achieved with the larger turbo and turbine here is a positive 12.5%. This helps scavenge the end gases out of the cylinder, and it helps that boost to back pressure ratio gain helps the engine scavenge ratio, which went from a negative 3.4%, exhaust manifold pressure being higher than intake manifold pressure, to a positive 8.7%. This is really favorable. And you see that in cylinder fill. The cylinder fill percentage went from 82.4% to 85.2%. We've got less air density, but we've got a better fill percentage. So now we can look at the cylinder air density. This is what determines power output at any fixed air-fuel ratio and constant RPM. Due to this improvement in cylinder fill, the cylinder air densities are virtually equal. So now we go to engine CFM displaced. This is the volume of this air density displaced by the engine per minute. We're up to 444 where at the same air density, we're going to make some more power. Mass airflow is the bottom line. We went from 94.9 pounds per minute to 104.3 pounds per minute. And our torque remained constant. So all the things we've talked about were all done in order to do this. And we nailed it. We virtually nailed constant torque, which was our goal in the first place. So the math tells you how much air mass you're flowing through the engine. The I dash tells you how you did it. So what's next, guys? Is it compounds? Is it water meth? Is it nitrous? Leave your comments down below because I'm going to be reading them. Because one thing is certain, eventually this engine is going to go bang. Oh man. If somebody told me I was going to make 1,000 horsepower, I'd have told them they're nuts.